Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And we're going to start a little 9-part mini-series on one-way fixed ANOVA. The first one deals with model development. The experiment has one outcome and one factor with A levels or treatments. A is a number, so it could be 9 levels, 9 treatments. An example outcome is tensile strength of cement, and tensile strength really means like how much strength to break it apart. And the factor is the mixing technique, and there's 4 different mixing techniques, so there's 4 levels. Another quick example is outcome is brick density. The factor is oven temperature, and the company will test 5 different temperatures. So that means 5 levels or 5 treatment groups. Notes, the number of observations within a level is replication, denoted by N. So at these 5 levels, there may be 10 observations within each of the 5 levels. So the N would be 10. Because there's 10 replications within each level. Randomization refers to randomly assigning observations to a treatment combination and then randomizing the order that the experiment is conducted. So let's look at some nomenclature here. And this is the way my mind thinks about it. I like it in columns. Now, I've seen tables where they have it in rows. Either's fine. So if this is the factor, for example, oven temperature, and these represent the different temperatures of the oven when studying brick density, how thick the brick is. These are the observations, so there's N replicates in each level. And so the first index represents what factor level. So factor 1, factor 2, or level A, I should say, level 2, and then the second digit is what observation within that level. So 1, 2 to N, 1, 2, 3, 4 to N, etc. Now, if we were to take and add these, that's what the dot represent. It means that you're summing over that index. So we're holding 1 fixed, so we're in level 1, but then we're going to add up the observations. And you can do that for each level, and that's called a treatment group sum. So the ith treatment group would be yi dot, means add them up for that in that level. And then we can add them up and then divide by how many there are in each level, and that would be the treatment group mean. So the first index is level. The second one says we've summed over that second index, and then we're going to take an average. And so it's the same, but then we're just dividing by N to get an average. Now, if there are 2 dots, it means we've summed over each index. It means we're summing everything, and it's this. And if we put a bar above it, then it's a mean. So we've summed everything, but then we've taken the mean. And since there are A levels and each one has N observations, then the mean, it's the sum is divided by 1 over N times A. Now, here's the model in scalar form. Yij is equal to mu plus tau I plus epsilon ij. So I being the levels or the treatments or the groups goes from 1 to A. The number of observations in each level or each treatment group is 1 to N. Yi is the response from observation J from treatment I. Mu, tau 1 through tau A are fixed unknown parameters, and the epsilon term is the error. And the standard assumption is that they have a mean of 0, constant variance sigma squared, and uncorrelated. The normal assumptions are the same as the standard assumptions except for they're normally distributed. And we need this when we do hypothesis tests and confidence intervals. Matrix form is going to be similar. It's y equal x beta plus epsilon. Those are vector signs because like y holds all the response data. It's NA by 1, so it's a very long vector. X is the design matrix, and it's NA by A plus 1, has a rank of A, so it's actually not full column rank, and you'll see why in a second. And we have to have at least n equal 2 or more. The standard assumptions is that our error term is normal, or not normal, mean 0, constant variance sigma squared, covariances are 0. The normal assumption is that it's multivariate normal, mean 0, covariance matrix sigma squared times I. Now, some will write a normal and then tell you the index says how many, how big is it. So it's n by a. So it's n by a. So this is an n by a 0 vector, and this is an n by a covariance matrix. The design matrix, first column has all 1, so that's a 1, so it's a vector of NA, and perhaps I should have a vector sign above that. Now the first n observations are only in group 1. So when we do this multiplication, it's going to pick off these first 2 n times. And then we move to the second group, and it's going to, then that's 0 and this is 1, it's picking off the second, tau 2 in the same way. And so this is the design matrix. Notice that if we add up these A columns, so column 2 through column A plus 1, it equals this. So it's not full column rank, but it's rank A. And here's a point that will be made later. If we take the span of this matrix X and create all possible combinations of the columns, we get some sort of vector space. But if we were to leave this first column off and then just take the span of these A columns, we'd actually get the same vector space because this is a redundant vector. It's dependent, it's not a set of independent vectors. But these are A independent vectors. So then let's look at the projection matrix onto the column space of X. First notation, U, and then subscript n by n denotes an n by n matrix of ones. Unitary or unary, that's the matrix of all ones. And it can be thought of as this. U n by n is actually a 1 vector of length n times a 1 vector of length n. So this is a n by 1, and then this is 1 by n because of the thing, and it creates an n by n matrix of all ones. Now the layout of the perpendicular projection matrix, and we've been calling it M in previous videos, and we'll continue to call it M, is X transpose X, generalized inverse X transpose. Now the layout of it is this. It's what's called a block diagonal matrix, where in the block it's a constant matrix of 1 over n, right? So this is an n by n matrix of 1s, but we have to multiply in that 1 over n. And so each block down the diagonal is a matrix of 1 over n by n matrix of 1 over n. Now let's prove that, because that'll be important. So let's let X star be the design matrix without the first column. Now this notation here is actually using the R software notation. So we want all the rows from 1 to NA, so that's all of them, but we only want the columns from 2 to A plus 1. So really it's the design matrix with the first row picked off. So the first column's removed. And as I mentioned earlier, the column space of X and X star are going to be the same, because that column of 1s was really a dependent vector or a dependent column. So X star is NA by A, and it has a rank of A, so it's full column rank. And that means X star transpose X star inverse exists. And when you do this multiplication, you used to get a diagonal matrix of n. And I'm going to let you do that on your own because it's pretty straightforward. And so that means the inverse is diagonal with 1 over n. So the perpendicular projection matrix onto the column space of X star is X star transpose X star inverse, X star transpose. And then again, I'm going to let you do this, but it can be easily shown to be block diagonal of 1 over n u n by n. But since perpendicular projection matrices are unique on a particular vector space, and the vector spaces spanned by these column spaces are the same, so that says the perpendicular projection matrices have to be the same. So M must equal M star, and that's the end of the proof. A few notes, and we've looked at this in previous videos, but I'm going to write it down for this mini series. M is idempotent. That means M times M is M. The rank of M is the trace of M. And actually this is because it's idempotent. And if you were to look at the trace of M, that means add up all the diagonals. But there's n ones here, and so if you add those up, you get n. There's n ones here, n ones here, and there's a of those little groups. So the trace, you know, the sum of the diagonals is 1 over n times a, which is just a. So that's the rank of M. And we kind of knew that going into it because of the column space, you know, has the dimensions of a. Now, if we look at M times y, remember this is the y vector, so it's an NA by 1 vector. Then you're multiplying it up to that block diagonal. Each little block just picks off its own little section of the response variables, or the y. So you get the sum of the y1 dots, n times. So this is a n by 1 vector of 1s, and then as you move down, it picks off the next, only the group level 2 or group 2 response variables, etc. But then this n comes in and then makes them a mean, and we call that y treatment bar. It's the means of each treatment. So it's however many observations are in level 1, the mean, repeated that many times, same way going down. Now, the perpendicular projection matrix onto the column space of 1, so this is an NA by 1 vector. So this is the first column in the design matrix. So if we look at the column space of that, well, it's a constant. The column span is all constant vectors. But let's look at the perpendicular projection matrix onto the column space of this 1 vector. So you take, it, and then 1 transpose 1 inverse, 1 transpose. Now this inner piece creates, it's summing NA1, so it's NA, but then you take the inverse, so it's 1 over, and then that can be moved out, and then 1 transpose is UNA times NA. So the projection matrix, so the J is a projection matrix on a column space of 1, which is all vectors that form this constant 1. And since 1 is part of the design matrix, the column space of 1 is a subset of the column space of X. And it's just a constant matrix of 1 over NA. Now, this becomes important when we start looking at contrasts, because we want orthogonal contrast, and it ends up being the set of orthogonal contrasts lives in the column space of X but are perpendicular to this column space. And well, more on that I think in video 8 actually, or in part 8. A few notes: J is an N by A by NA constant matrix with all entries 1 over NA. J is idempotent, so the J squared is equal to J. The rank of J, since it's idempotent, is the trace. And if you add up the diagonal matrices of the constant matrix, you get just 1. If we look at J times the Y vector, remember that J is this. So this is just a constant matrix of 1s. So when we do this multiplication, we're adding up all the Y's. And then we do that for each row. So it's the sum of the Y's, but NA times. So it's a constant vector. But then if we divide by 1 over NA, that becomes the grand mean. So this constant vector is just the grand mean repeated NA times. And one note though, remember, so this Y, I think of it as a dangling Y. It's out there in NA space somewhere. Now if we pre-multiply it times J, since J is a perpendicular projection matrix on a column space of 1s, it's going to shove this Y vector down into that column space. But the column space is of the form K times 1. So it has to be a constant vector. And that's what we're getting here by this, right? It's a constant vector. And so it's doing its job, basically. Okay, well, that's all I have for part 1. And there's going to be 8 more parts in this playlist. Generalized linear models, design of experiments, and this little mini series is going to have 9 parts. So I hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.